So our main task is to look at derivatives. So starting derivatives of trig functions. Okay. The basic ones that we don't even do any derivation is the derivative of sin x. This is obvious. We just write it. The derivative of cos x, we just write it. The derivative of tan x, this one we also just write it. And then the fourth one, the derivative of sec x, we also write it. It becomes sec x tan x. And then the fifth one is the derivative of cosec x, which is negative. These, they move like that. And the derivative of cot is equal to negative cosec squared x. If you happen to forget any of these derivatives, apart from 1 and 2, you could derive them. For example, the derivative of tan, if I forgot it, I would say it's the derivative of what? Of sine over cos. Okay, meaning I need to use quotient rule. So I'll first have to differentiate sine and then multiply by cos, subtract by, I differentiate cos, then multiply by sine, and then I would divide throughout by the cos squared. So you understand the derivative of sine is cos, so there would end up having cos squared. And then this guy gives us a minus sign, so end up having a plus sine squared. Then I would divide by cos squared. So that would be 1 over cos squared, which is equal to sec squared of x. So you see, every time you forget n of them, if I forgot the derivative of sec, I would say, okay, this is simply 1 over cos. So again, we're using quotient rule. So we'll differentiate 1, multiply by cos, subtract, differentiate cos, multiply by 1, and then divide by cos squared. And that would be derivative of 1 is 0, derivative of cos is minus, so end up having a plus sign over, so I can write cos squared as cos x multiplied by cos x. And then on top there, I would multiply by 1. So I'll have sine over cos, which is tan, 1 over cos, which is sec. And so the product could be written in n order. It's the same thing. Okay, so that's how you would try to remember in case you find yourself forgetting these derivatives. Then the other key things that we need, the most key ones now, is maybe a situation where we are dealing with the derivative of sine of a function inside. Okay, so this derivative is going to be the derivative of that function inside multiplied by the derivative of sine, which is cos, and then we put the function. Okay? So I'm running through all of them. I'm doing the general case now. Suppose I have a function inside, the derivative of cos g x. This is going to be the derivative of g multiplied by sine of that g. You see? And then I come to the third one, the derivative of tan where I placed the derivative of tan of gx. That should be g prime of x multiplied by sec squared of gx, like that. So all of them, whether it's the fourth one, it will be the derivative sec g, that will be g prime, and then I'll have the product sec g tan g. So for all of them, that g never multiplies outside. It only comes out once, and then it appears in the cosec g cot g. Okay? I want us to be sure that this thing is on. So you don't need to make any mistake here. Whenever you put a function inside, what you do is you differentiate the function, and then you have the cosec of gx, and then you have the cot of gx. So there will be a minus there. And then the sixth one, the derivative of the cot of gx. So it will be the minus g prime of x, and then we get the cosec squared of the gx. Any function that is inside there. Yeah, that's what you do. Okay. Now, after you've done these general cases, then we move to the inverse trig. So I want to differentiate the functions y is equal to arcsine. Arcsine x is the same thing as saying y is equal to sine inverse of x. Okay. Or I would say the question is just similar to all other questions. And I'm doing this. So to avoid the confusion, in fact, I'm going to go straight now for this case. I don't want to use x inside. I want to use a general case, so I don't come back for the general case. I want to use a function g. So I'll use a function gx inside. Okay, so these ones we don't memorize, we drive. So you let theta be sine inverse of the gx. Now you understand that if you find that theta is equal to sine inverse, it's the same thing as sine of that theta equal to the gx. Now you agree with me that on the triangle, just when you reach here, you make a right angle triangle where this is your theta. And then now we know that using SOHCAHTOA, sine is opposite of hypotenuse. So opposite is gx. So this is like sitting like this. Then there one. And then the adjacent is going to be the square root of 1 minus the g, the whole g squared. Okay, so we need to differentiate the theta with respect to x. But look at where theta is when it comes to the second function. So theta is sitting in sine. So we use implicit. So we differentiate sine and get the cos of theta, and then d theta at dx. And then differentiate g, we get g prime of x. So we're looking for d theta at dx. So it will be g prime of x over cos theta. But what is cos theta? So cos theta, cos is actually adjacent over hypotenuse. So it will be cos theta from this comes out to be the root of 1 minus g of x squared over 1, okay, which is just the root of 1 minus g of x squared, like that. So we come and put it here. The square root of 1 minus the g of x squared. So this will be the general formula for any arc inverse that you're going to have. So you can check. So here I'm giving you these general ones, and then if you check the Cherry sheet, you find that when they want you to differentiate this, it won't just be sine inverse. It will be mixed in some things, and then you understand that, oh, now I need to use the general one. And in most cases for second year courses, it's rare to find only x inside there. They ask you like sine inverse of x. That's the rare thing. There's always a function inside. So we go to the second one. If I say f of x is equal to cos inverse of gx with the same derivation, it will lead us to g prime of x. The only difference between the two is that this one will give us a minus. Everything else will be the same. Okay. And then now, the third one, want to do f of x is equal to arctan of gx. That is, you let theta be equal to tan inverse of gx. Simply means I'll have tan theta is equal to gx. So we know that on the triangle, G will be here. Sorry, not G there. Theta will be here. Now tan is opposite over adjacent. So this will be G, and this will be adjacent. So meaning that this guy is going to be the root of 1 plus gx squared. Meaning we differentiate tan, we get sec squared of theta and then d theta at dx. And then this will be g prime. So meaning we'll have d theta dx equal to g prime of x divided by sec squared of theta. Now sec squared theta comes from here. Sec is hypotenuse of adjacent. So adjacent is 1. So we just have the hypotenuse, and then it is squared. So when you square our hypotenuse, it will remain as 1 plus. Oh, why do I put g prime? Gx. Yeah. So it will be like this. So it's very, very important that we know them in the general sense so that we don't struggle whenever they are needed. Okay. So with the same derivation we could get for sec inverse, cosec inverse, and tan inverse. But now we'll have to list for hyperbolic trig. One, the derivative of the hyperbolic sign is simply the hyperbolic cos. Okay. The derivative of the hyperbolic cos is the hyperbolic sine. 3, the derivative of the hyperbolic tan is sec squared x. 4, the derivative of the hyperbolic cot is going to be negative this guy. And 5, of this guy is going to be negative cos, like that. And the 6th one is for sec, is going to be the same. So these, they don't change at this point. They are almost similar. So the only difference we have between these and the hyperbolic and the original cos and sine is on the initial one. This one, fine. But this one, remember, for the cos and sine, we are going to have a negative here, but we don't have it. Okay. Simply because by the time we are driving them here, we use the approach that comes from the exponential functions. Yes. So that if we do the general ones, that's where we say, okay, the hyperbolic of a gx. This is going to be g prime, and then the hyperbolic of the g, like that. The hyperbolic of this guy, gx, that's going to be g prime, and the hyperbolic of the g. So these are what you're going to be using when we attack the Taylor sheet. You'll see that it's easy if you know them in the general cases. It's easy to run through because we will find them mostly as that. Okay, so nothing changes really. It's just that multiplication by the derivative of the inside function. Okay, so everything else can be done in a similar manner. We talk about the logarithm. And exponentials. So we have one. If we say find the derivative of ln, x, this is simply 1 over x. How do we get it? Find the derivative of ln gx. So you differentiate the g and then divide by the g itself. That's what we've done in the first place. When you differentiate x, you get 1 and then divide by x. Okay. A tricky one is where we say, okay, can you differentiate the log a of your g? Okay, here you would first convert the function. Okay, you would first convert the function to ln. So you would say ln of g, and then because I've changed the base, so I'll have a ln a down. So I'm changing the base from a to e. So I've log eg, log ea. And then down, it just becomes the constant as it is, and then I differentiate the function, which is g prime x over gx. So you as well want to write it like this. A gx ln a. Sometimes you find it written like that. So that's basically how you would handle the logarithms functions. If you don't find that it's ln, you find that it's a log. So that's how you deal with the log. And then can be asked also to find the derivative of an exponential function, ex. It will be ex itself. How? Coming from here, eax. So I differentiate a and multiply by the whole function. So I differentiate ax, I get a, and then multiply by the whole e ax. And then what happens then if they ask me to differentiate a to the power x? When we put the general one, a to the power gx. Okay, so I would first say, okay, for this one, I want to let y to be my a to the power gx. Then apply ln on both sides. So I have ln y, or have ln a to the power gx. Meaning, I have ln y. Since ln drops the power, it will be like that. Then differentiate ln y, I'll get 1 over y, and then dy dx. Then here I'll differentiate the g, then multiply by the ln. Since ln is just a constant there, meaning the dy dx is going to be multiplied by y. So multiplying by y means, our y is a gx, then by g prime, and then ln a. So this will be the function, like that. So you don't get much worried there. So you get them as in the general cases. Then now I can freely say we can now go to the Tutorial sheet and start doing questions, because the derivative part, this is what we really worry about. The other pieces of differentiating polynomials is not a big issue. Differentiating quadratics, any power of x, those are easy things. But what is always tricky is how the application of trig comes in. The differentiation of trig, especially the inverse trig, and then hyperbolic. There's no part where the question demands that we drive the derivatives. So the driving here was just trying to help us remember, in case you find yourself forgetting the derivative of arc sine, or the derivative of arc cos, or of arc tan. If I happen to forget, then I can remember to still drive it and then use it. But you find in most cases, if I can remember it, I just go straight and use it. Okay. The same with this, you don't drive, you just use. And then these also, you don't drive, but here we've done the derivation so that we don't forget. That's the key thing. So in our class for tomorrow, we'll start answering the Tutorial sheet. So we'll be using more of those questions there. We'll be doing some additions, and as we explain concept by concept. I think this should be enough for the basics. Okay, bye-bye.